Hello, welcome back. Today I will start my series about volume of solid revolutions. Pretty much it's having a function or a line going around an axis. Now for today's lesson we're going to understand how integrals work and some knowledge of geometry. Alright, so before we actually get into the hard stuff and calculus, we must understand the idea of a cylinder and its volume. So here we have a typical cylinder, and I ask you, how do you find the volume of the cylinder? How much can it hold? Well, if you think about it, the cylinder is pretty much made out of these discs or circles, you might think, and each circle has an area, of course, right? This area is simply pi r squared of each little circle. Now, if you look, each little circle has a little width. Now, if you stack all of these circles, you actually get a cylinder. Now, you would just multiply all the areas times how many of these things are stacked. In other words, what is the height? So, volume simply equals pi r squared h. Now, we can actually apply this idea to more advanced concepts. In other words, solid revolution. So, for example, in this diagram we see how we have pretty much a cylinder, but just slanted horizontally. But now, it's still a cylinder. We can actually get these representative circles that we were talking about, which are super useful. So, first I have to ask myself, what is the radius? Because to find the area I need the radius. Well, assuming that this is the middle to the line is r. In other words, all I have to do is pi r squared gives me the actual area of this representative circle. Now, you can take an infinite amount of these little representative circles, but each representative circle is very important in the manner that it has this small amount of width. It's very insignificant, but it exists. In calculus, we formally denote it as dx. Now, we know that we have an infinite amount of these circles, like we've proved before. Stacking them simply will make a cylinder. So here, in the same way, if you stack these circles, you'll make the complete cylinder, or in other words, the volume of revolution. So I would just have to add all of these together, and a summation is needed, an infinite summation, and pretty much I assume knowledge of calculus is present here, and I would immediately go into the integral. Pretty much means I'll have to take the integral from initial point A to final point B of pi r squared dx. Now this makes a lot of sense. This actually will give me the volume of this shape from revolving it. Now, it's not as easy as this problem. Usually, many problems in calculus and real-life applications don't have this simple slant line, but instead we have a slant, this simple horizontal line, I'm sorry. In this case, we have a slant line. Now, it's very important to understand what happens to the radius. Well, the radius in this point, we see it's okay from here to here, but however, the second radius from here to here is much bigger. There's a difference. How do we account for this radius? We can still write pi r squared, pi r squared, pi r squared, but we know each radius is different. So, we must take something into account. If we choose a point right here, let's call it x1, and then we see what the y counterpart is in the function, it'll just be fx1. So you see, whatever input I have right here, I'll always have an output in my desired function. In other words, this height is just f of x. So pretty much, for example, if this line represents some function, and we choose a certain x value, we'll see how high it is. And this makes perfect sense because f of x is changing. So in other words, this radius is obviously going to be different from this radius. So we can make a very important conclusion. In this case, r squared equals f of x squared, because f of x represents the radius from this point to this point, the height from this point to this point. Okay, once we've established this, we go to this same idea. We have this area now. We can write as f of x, squared, pi squared. But now we have this small amount of width, dx. Although it's almost insignificant, it's there. And we have to add all of these together to get a meaningful volume. So we can write integral pi squared f of x squared dx from a to b. Now this is the typical formula for, and it's called the disk method, because as you see, these representative circles that you're making are actually disks. So when you add all of them together, you can actually get the volume of a solid revolution. This concludes my first part, and I would follow up with washer methods, shell methods, and even slant line revolutions. Thank you.